Okay, so given a group, I'm going to define the center of the group, usually written capital Z of G. And this is a subgroup of capital G, and it's Z for reasons I can't remember right now. So what is this? Well, G is in the center of G, capital G, if and only if the following conditions are met. For all x in the group, xg equals gx. So we say that G commutes past everything. Past everything in the group. That's how you express it. That's what it is. There's a slightly easier way, or slightly better way of writing it. You can say that for all x in the group, well, we can take this relationship here and multiply on the left by x minus 1. G equals x minus 1 gx. I guess we could also multiply on the right by g minus 1, and we could say for all x in the group, x equals gx g minus 1. And of course you can swap the locations of the minus 1's there. You can also say it's equal to x gx minus 1 if you wish, for a different x. Okay, well that's the definition of it. It's the centre of G. Every group has a centre. And it's a nice, interesting subgroup to consider of any group that you've got. So you might be looking at a new group and you might say to yourself, right, what do I know about this group? Well, let's work out the centre. Well, I guess we better prove that Z of G is in fact a subgroup, How do we do that? Well, if G is in the centre of the group, we need to show that G minus 1 is also in the centre of the group. And I guess that's the first thing we have to prove. And the second thing we have to prove is that if G and H are both in the centre of the group, then we need that the product GH is also in the centre of the group. And we can do that relatively easily using this formulation here. So we know that for all x in the group, G equals x minus 1 gx. And so all we do is take an inverse of that. G minus 1 equals x minus 1 gx all to the power minus 1 equals x minus 1 g minus 1 x minus 1 minus 1. You'll see that to take the inverse of any element, if I go a, b, c, d to the minus 1, you'll remember from, I forget which screencast it was, that's equal to d minus 1, c minus 1, b minus 1, a minus 1. And of course, and you can verify that simply by multiplying a, b, c, d by d minus 1, c minus 1, b minus 1, a minus 1. You'll see how I've taken the inverse of each element separately and written them backwards so that they all cancel out in pairs from the inside out, I guess. So what does this show us? Well, we've started with this, which is the definition of the centre of the group, and we've ended up, simply by taking a group inverse of that, we've ended up with G minus 1 equals x minus 1, G minus 1, and of course x minus 1, the minus 1 is just x. Proved. Now we need to show this character here. So what we've got is, yeah, sorry, a bit of a glitch there. So what have we done? We've proved that if G is in the centre, then G minus 1 is in the centre as well. So we've got that. We've done that one. So now we need to show that the product of any two members of the centre is in the centre. Okay, well let's just try that. So if G is in the centre of G, and H is in the centre of G, well we ask, what is x minus 1 GHX? equals what? Well, it really ought to be equal to GH if, oops, GH, if GH, the product GH is in the centre. Well, this looks quite difficult. Well, you need a trick, basically. You write it like that, x minus 1 G HX, and then you insert the identity element in there. And then you rewrite the identity element as this, x minus 1 G x minus 1 hx. You've rewritten the identity element, which is there. You've rewritten it as x minus 1, which is perfectly legitimate. And then you re-bracket it, x minus 1 G x minus 1 hx. And you know that G and H are separately in the centre. So you know already that, you know that x minus 1 gx equals G, and you know x minus 1 hx equals H. By definition, because you have specified here that G and H are in the centre. And of course, that's equal to G because we know this, and that's equal to H. So the whole thing is equal to GH. So summarising, if G and H are in the centre, oops, that's a normal G, then we've established that GH is a member of Z of G as well. Therefore, Z of G is a subgroup of G. Yeah, there it is. GH is a subgroup of G. And the centre is always an interesting thing to consider. Always an interesting thing to consider, and I'll give you some more details on this and some examples in the next screencast. I'm going to stop there.